So this is Holy Cross Mock for component 1, and it's Mock 1, and we're on to question 3, photosynthesis. And again, there's no tricks in this question. Pretty straightforward photosynthesis question. List 3 photosynthetic pigments, so 3 different pigments. The chlorophylls and the ones that any others that you can remember. So chlorophyll A, we could say chlorophyll B, xanthophyll, carotenoids. So any 3 of those will do. What's the advantage to the plant of having more than one of these? Well, these all absorb light at different wavelengths. So if you've got more than one, you can absorb more light in total, which is useful. So this allows light of different wavelengths to be absorbed. Explain the term action potential, just a definition that you have learned. So the key thing here, this is action spectrum, and you've got the name of the other one, absorption spectrum, below, so you need to get the right one. I always think action, well, it's the actual thing that you are kind of measuring when you do experiments. So this is the rate of photosynthesis, and what's it against? It's against this thing at the bottom, which is the wavelength. So at different wavelengths. Here's an absorption spectrum. So this is how much light gets absorbed by the pigment, and that's the axis on the right. So again, lots of light being absorbed at wavelength 650 by chlorophyll A and so on. Not much in the middle where it's green. Draw a line to show the action spectrum. Well, we need to label the axis. Well, we've already given it in the definition there. So the axis is the rate of photosynthesis. And draw a line. Well, we're not expecting you to be kind of absolutely brilliant drawing this line, but basically where these peaks are, they kind of coincide, so we're gonna go that sort of thing. So really the line drawn to show that the peaks coincide with each other. It's wanting a little explanation of this. What does this relationship tell us about light and photosynthesis? Well, the wavelengths most absorbed, our black line, well, they're used in photosynthesis, and they power the sort of chemical reactions. So the wavelengths of light most absorbed are the ones used in photosynthesis, or the reactions in photosynthesis. Here's a diagram of which you should recognise kind of ups and downs and things like that, and they've got lots of mystery kind of letters on here. 1 and 2, you should hopefully recognise those. You should already be in your mind thinking about what some of these things are, you know, what gets raised up and then drops back down, what this thing here is giving things to that and giving things to that and giving something away as well. So we've got water being split there. It's giving something to these photosystems. So giving electrons away, and something up there that's being a H, that's the protons. So you should be able to figure out what's going on there. Name the light harvesting units. Well, these are photosystem 1 and 2. So these are photosystems. Name the process by which Y is broken down. Well, we've suggested this is water. So breaking down water, that's our photolysis. Name X, Y, and Z. Right. X becomes X with a hydrogen, or a couple of hydrogens attached to it. So it's carrying this hydrogen. So these are our hydrogen carriers, or our name there, that is our NADP. Remember P. I always associate P with photosynthesis, that sort of idea. So X is NADP. Y, yes, we've already suggested that's water. Z, well, when photolysis, water gets split up into the hydrogen ions, the electrons, and oxygen. The oxygen is a waste product, and electrons go and do something useful. So that looks like it's electrons going up there. Z must be our waste product, oxygen. Oxygen there. Name particles. This is giving you a little clue there. So these are not kind of elements or molecules, particles. So the only particles you know are, if you do biology, are kind of, protons, electrons, maybe neutrons might have been mentioned at some point. So one that goes from water and drops down and then goes up again from the photosystems, that's got to be electrons. Q, so let's just put that on our little diagram. So E minus there, E minus dropping down, E minus up there, dropping down, and this is kind of powering chemiosmosis. Remember the first question? And Q, well, that's the only other thing left. That must be our hydrogen ions, or protons. So protons, or H plus there. We could have had H2O there, and we could have had oxygen there. So naming those, hopefully if you've learned this cycle, these are kind of marks that you're hoovering up. What is the function of A1 and A2? Where's A1 and A2? A1 and A2, they're where the electrons are going to and then dropping down. So they are kind of taking the electron and booting out the electron again. So posh biology words for that are they're accepting the electrons and donating them again. That's just what we're going to kind of put. Accepting or donating electrons, and the electrons are going to go down the electron transport chain. Which of the compounds shown is used in the light independent stage? So light independent stage, we're talking about Calvin cycle, and things coming out of this diagram, there's only a couple of things coming out of this diagram. We've got oxygen coming out and this thing here coming out. Everything else is within the cycle. So which one of these is used in the light independent stage, the Calvin cycle? Well, it's not oxygen, because that's the waste product. it's going to be this up here. So the compounds shown, so XH2 is the one that's shown. You know the name of this, so it would be NADPH2, don't worry about the 2, or reduced NADP. But on the diagram, XH2 is the one that's actually shown, and that's going to go off to the Calvin cycle. Why? Well, because in the Calvin cycle these H's are actually going to be useful, because we've got, in the Calvin cycle we have got essentially CO2 going in, and we're making eventually glucose. And so what's missing? A H. Well, that's where the H is coming from. So this is a source of hydrogen reducing power for CO2, that sort of thing. So source of reducing power, or hydrogen. Now we're going to add hydrogen to, if you remember the whichever part of the cycle it is, we're going to add it to GP, to make TP, or other words, this you might say this differently as PGA, GALP, depending on which textbook. These are the GP and TP are the ones that we actually use. So a little bit more difficult at the bottom, but you should really have got the bulk of this. You should really be able to tell the difference between these two graphs and give the definition, and certainly name your pigments. So that should be a high scoring question, 17 marks.